All right. So we're looking at 8x squared plus 4x minus 1 equals 0. Put that over here. Actually, I like writing it like that better. That's the function. It's equal to y. Okay? Now, how do we complete the square and put it in vertex format? Remember what the general format for vertex format?
Isn't it
A times what?
Isn't it, oh, A times,
X minus
H. Okay, yeah, now I remember.
All right. The reason you need to know this, or the reason you always need to remember this, is because it tells you how to do this problem. In other words, I want to put that function into this format. And the way I'm going to do it is by completing the square. Because when you complete the square, you end up with a polynomial that can be represented as an x minus some number quantity squared. So that's why we do this by completing the square. Okay, what's the first thing I need to do to complete the square here? Work me through the process of completing the square.
You would take the square root of 4.
Hold on, let me write this up here so that I can write my other stuff down below. That's what we're trying to make this function look like. First thing to do is put parentheses around that. I left that space intentionally. Okay? And the reason is that I'm now going to complete the square inside the parentheses. And whatever I complete the square with, I will balance out by adding or subtracting the same number from the same side of the equation. Then it will look exactly like this general format. And that will be helpful because then I will know what H and K is, and A, whether it's positive or negative, will tell me whether it opens up or opens down. And that'll tell me whether it's a maximum or a minimum. So completing the square here is definitely a valuable thing. It tells us a ton of stuff. What's the first thing I have to do inside the parentheses before I can complete the square?
Would you divide by 4 first?
You're close. You factor out the coefficient of the x squared term, always, no matter whether it's a factor or not. You do it. In other words, that could be a 5 and not a 4, and it wouldn't matter. I would still divide both terms by 8. I cannot complete the square until that x squared term has a coefficient of 1. Okay? So I'm dividing out 8. What's my second term going to be?
1/2 x.
Leave room. Now check. Have we changed anything?
Yeah, so...
No, we haven't. When I say that, I mean we have not changed the function.
Okay.
If I multiply the second line, if I distribute that 8, I get back to the first line. That's what I mean when I say we haven't changed it.
Okay.
We haven't changed the function. Okay? The only thing we've done is manipulated it such that now I'm in a position to complete the square. Well, how do I complete the square? And you always are adding a number right here. How do I, what do I add there? How do I do it? It has something to do with the coefficient of the x term.
Would you add 8?
Not quite. You take half of this, which is what? What's half of a half?
A fourth.
And then square it.
Whatever fourth squared is. So that'd be 1/16.
Huh? Yeah, don't try to figure out whether it's a number that's pretty or not. It's whatever it is. Okay? And sometimes these get ugly. And sometimes you can have really rough fractions. That's why I say you are not dividing a greatest common factor out from this original function. You are dividing out that coefficient of the x squared term, whatever it is. Okay? Now, when I wrote that in there like that, in order to counterbalance it, I got to figure out how much I just added to the right side of this function. How much was it?
What you added to the right side of it. You just added 1/16, didn't you?
Well, I did, but notice that it's being multiplied by an 8.
Okay.
So what did it really add?
The 8
okay.
times 16.
8/16, which is what?
Just 1/2.
Okay. So I have to subtract 1/2 also to the same side of the equation. Now, if I were to do all the math, that would still be exactly that. I have not changed the function, and that is the whole goal. Every time you go from one row to the next, always make sure at every step that you have not changed anything. Because all I did was add 8/16 and subtract 8/16. Well, that doesn't change the value at all. Now I'm really close to being able to put it into this vertex format. Notice how, what is y going to be? 8, there's my a.
Okay. Oh, A, okay. And then...
Remember, it's got to be a linear term, so it's just an x. In this case, what's the rest of it? Remember when you took half of that term?
Yeah.
That's the rest of it.
Okay.
Plus 1/4. And whether it's plus or minus depends on that sign right there. If that sign is minus, then it's minus. If that sign is plus, then it's plus. And I need a squared there.
Okay.
And what I'm saying is that this term is identical to this term. And that's the whole point of completing the square, is that so you can write it as a linear term squared. Now what's the rest of it?
Minus 1.5.
Like ratios. Improper fractions are much more beneficial to you than proper fractions. Now is the only thing they ask. First of all, I'm going to ask it, where's the vertex? We went to all this trouble to put it in vertex format, Remember, that's what that is vertex format. So what's the vertex?
Is it the 1/4 and then -3/2?
Notice the standard is x minus h. H is the
so -1/4.
Exactly. In other words, h is a -1/4. That's how it got to be x plus 1/4 here. And k is a -3/2. So that's the vertex. Now the question is that a maximum or minimum?
Minimum.
Correct. Why?
Because they're both negatives?
No, that's not why. Because I could have a parabola that looked like that, where the vertex would both be negatives, but I'm looking at a maximum there.
Okay. Oh, is it because there's not a negative in front of...
Yes, that makes it a minimum. In other words, it's a parabola that's opening up going with the plus sign. When A is a plus number, then the parabola is always going to open up and you're always looking at a minimum. When A is a minus number, the parabola is always going to open down and you're always going to be looking at a maximum. And that's all there is. If you notice that all quadratics graph is either that way or that way. So there's only one critical value there, and it's the vertex. And on the left, it's a maximum, and on the right, it's a minimum. So knowing the sign on A is critical. I tell you what, you need your thinking hat on today. I read through a few of these questions. These are by far the hardest questions we've faced.
Oh, good.
Yeah, I know. We're halfway through these questions, but at the rate that their degree of difficulty is increasing, we might be slowing down a little bit. So what y is the number of prisoners in the United States. And x is the number of years since 1980. So how many prisoners were there in the United States? And this is actually in thousands.
Okay.
Just in case it doesn't make sense. We can ignore that for the moment and just deal with this function. But let me ask you, how many prisoners were there in 1980? Remember what x is. X is equal to the number of years since 1980.
So there are 22,000?
What's x? When I say how many prisoners are there in 1980, what is x?
Oh, is it 0?
Uh-huh. Now
Okay.
plug in 0 for x, and whenever you're looking at a quadratic, when you plug in 0 for x, you get rid of that first term, you get rid of the second term. The only thing left is that. So the answer is 320,000. Because it's in thousands. Yeah. Okay. So that's how many prisoners there were in 1980. In 1981, x would be what?
1.
Okay. And we would plug it in and we could tell that it's going up, right?
Yeah.
Okay, they want to know what is x when y is 505,000, which means I'm going to write it as 505. Nothing like them throwing in little tricks to try to make us make a mistake. In other words, it would have been really tempting to write that as 505,000. But notice the whole problem has to be in thousands. Let me ask you something. Are you allowed to use a calculator on this test?
Yeah.
Any calculator?
Yeah, I think so.
Okay. So what are we going to do here? In other words, they want to know what year the inmate population hits 505,000. So don't I have to solve that for x? And whatever answer I get for x, add it to 1980, and that will be the year. Okay?
Yeah.
Now, they didn't make this an easy quadratic. First of all, if I had to solve this without a calculator, what would be my next step?
Subtracting 505?
Okay, so I get 0 equals 2x squared plus 22x minus 185. Now the reason I ask the question is because that is not easy. Maybe it's easier than I think. What's that? That's 5 times 37. So 5 and 37. 37's got to go there. The 5's got to go there. It's got to be a... Nope, that doesn't work either, unless I did my division wrong. 5 goes into 185 37 times. So the only factors of 185 can be 37 and 5 that make any sense at all. And they don't give us that middle term. So this is a ridiculously hard factoring problem. You know how to solve this in your calculator? What kind of calculator do you have, Madison?
The TI Inspire.
Do you know how to find the zeros of this function?
Yeah.
You graph it, and you find out what the zeros are.
Yeah.
As long as you know how to do that, that's the simplest way I know. There's probably 8 different ways on that calculator to find the zeros of a function. But that's our goal here. Just for the sake of time, let's pretend we're going to get 2 answers because we're looking at a quadratic, okay?
Mm-hmm.
So let's say I got an answer of x equal 25 and another answer of x equal minus 15, which might be 2 typical answers you would get. I was just looking at that to see if 15 was a factor, but it's not. Which one is extraneous?
The negative 15.
Okay, so this is our answer, but not to their question. What's the answer to their question?
So the 2005.
Right. Right. All right. Hang on to your seats. They get tough. But luckily, there's only 10 minutes left. Now, the following question. Everybody hates word problems, okay? And I pretty much tell everybody that word problems are actually very easy. Is all you have to do is start them out right. And the way you should start out every single word problem is by defining your variable and spelling out what it means. What is that variable? Okay?
Mm-hmm.
And then I tell them that the easiest way to figure out how to define your variable is to go to the last sentence first. Well, if you do that with this question, this is kind of a level 2 word problem. In other words, one would be tempted to say, what ticket price will generate the most revenue and what is the maximum revenue? Well, right off the get-go, I would say, well, let's let X be the ticket price. But that's not the way this is going to solve nicely. Notice that if you read the question, it says, however, for each $4 increase in ticket price, 20 fewer tickets will be sold. So let's say you own this theater, okay?
Mm-hmm.
And if you sell each ticket at $30, you're going to sell out 550 seats. So you're going to make $16,500. That's how much money you'll make. Now somebody comes along and they promise you that if you increase the ticket price by $4, it'll only cost you 20 fewer tickets. And in fact, if you increase it by $8, it'll cost you 40 fewer tickets. You won't sell out. You'll sell out 40 fewer tickets. But notice, you're selling each ticket for more money. So if we look at this problem of trying to maximize revenue, we kind of have to do it like this. Revenue is the number of tickets sold times the price of each ticket, right?
Mm-hmm.
So that's going to be a function that we're going to end up with. And then that's going to end up being a quadratic because that's part of algebra we're studying right now. And we'll be able to find out how to maximize that quadratic. It'll be a parabola, and all we got to do is find its vertex. And we'll know exactly where the maximum occurs. But back to the original problem, which is to spell out the variable. Well, only because I've seen a number of these kind of problems, whenever you're talking about ticket price increase problems, those are second level word problems. And let me just tell you that your variable you want to make is the number of $4 price increases. That's what X wants to be. And let me explain. First of all, my total revenue is the number of tickets sold. Well, I can now know that the number of tickets sold is 550 minus 20 times X. Because notice that if X is 0, my ticket price is still $30. I haven't increased it at all. And I would sell out all 550 tickets. But if X were 1, if I decided to make the tickets cost $34, then I'm going to sell 20 fewer tickets. And if X were 2, meaning I'm going to make the tickets priced at $38, I'm going to sell 40 fewer tickets. Well, what's each ticket price going to be? Isn't it $30 plus 4x? In other words, if x is 1, I'm going to sell each ticket for $34. If x is 2, I'm going to sell each ticket for $38. So, now I have my revenue as a complete function of x. Notice that I can multiply those two terms together and get a quadratic. And the quadratic is, I did this in 22, it's plus 2140 minus 80x squared. So there's our quadratic, okay?
Okay.
If you plug that into your Inspire, it will give you a curve. And that curve, we know, is going to point down because of that negative sign in front of the x squared. So the curve's going to look something like that. And right there, this is revenue up there. This is x. Wherever we discover that vertex, that will be the price that we'll want to charge because it will maximize revenue. That could be 1, 2, 3, 0, 10. Who knows? Maybe we should up it by each ticket price by $40 so that every ticket is $70. That would be 10 X's, which means we would only sell 350 tickets, but gosh, I'd rather sell 350 tickets times 70 than 550 times 30.
Okay.
Okay?
Yeah.
So anyway, that's the way this problem proceeds. And
Okay.
again, there's no point in us trying to do that manually. That's clearly a calculator problem. But notice that what they want to solve for is this value here. In other words, what is x that creates a maximum revenue? And then once you solve for that x value, then you can figure out what that revenue is. And you can compare it to what your revenue was if you didn't fiddle with the prices of the tickets.
Okay.
Okay? All right, Madison. Sorry these are getting so hard that we're not getting very far very fast, but I'm not quite sure what else to do. I could skip the really hard ones, but I'm kind of reluctant to do that. I'm going to try not to spend as much time on them as otherwise. There's no point in spending a half an hour on really difficult problems that you may not even see on your test. Okay?
Yeah.
All right. I'll talk to you next time.
Okay, bye.